Let's do the Chapter 6, Part 2, and Chapter 12 problem set. Number 7, a 10.0 kilogram mass is tied to a 3/16 inch manila line, which has a braking strength of 1.80 kilonewtons. What is the maximum speed the mass can have if it is whirled around in a horizontal circle with a 1.0 millimeter radius and the rope is not to break? Now, the 3/16 inches, that's superfluous information. But what matters here is that we use the Fc equals mvt squared over r equation for centripetal force. And if we do that, basically the rest is just plugging and chugging. We put in our givens and we find the speed to be 13 meters per second. Number 9, a baseball player rounds second base in an arc with a radius of curvature of 4.88 meters at a speed of 6.1 meters per second. If he weighs 845 newtons, what is the centripetal force that must be acting on him? Okay, so what we have here again is pretty much like the last one. It's plugging and chugging. The only little difference is that we do need to find the mass by dividing his weight by 9.81. Now the question also asks, well, what's supplying the force? This is an important question in these problems because it's one thing to know the magnitude of the centripetal force. It's another thing to know what's supplying it. And in this case, what's supplying it is the static friction of his shoes gripping onto the ground. Similar to the lab that we did where it was a static friction of the tires on the pavement. Number 19. A scale is fitted into the seat of a roller coaster car and a person weighing 800 newtons sits down on it. The car then descends along a path that has the shape of a 100-meter radius vertical circle, with its lowest point at the bottom where the car reaches its greatest speed of 40.0 meters per second. What is the maximum reading on the scale? Okay, so let's take a look at how we're going to set this up. We first need to get the mass. So the mass is 800 newtons divided by 9.81 meters per second squared. We get 81.54944 kilograms. And now we have to consider what is supplying the centripetal force. What is supplying the centripetal force? The centripetal force at the bottom of this big loop is going to be, of course, mvt squared over r. That's going to be the magnitude of the centripetal force. But let's look at what's supplying it. There are two things supplying it right now. There's the normal force, and the normal force is going upward. But then we have to subtract the weight because the weight is going downward. That's why it's Fn minus Fw. And so Fn has to be big to make up for that in order to be enough to supply the centripetal force. And so the setup becomes Fc equals Fn minus Fw. And we can replace Fc with mvt squared over r equals Fn minus 800. We know the 800 because we know what the weight is. Then we plug and chug and find that the normal force has to be 2.10 kilonewtons. So 2100 newtons is how much force is pushing up on his bottom as he's sitting there, right? That has to be a large normal force because weight is not helping. Weight is going in the opposite direction. Number 23. At a given instant, someone strapped into a roller coaster car hangs upside down at the very top of the circle of radius 25.0 meters, while executing a so-called loop-the-loop. At what speed must he be traveling if at that moment the force exerted by his body on the seat is half his actual weight? Assume that at the start of the ride the straps were fairly loose. They're telling you anything about the straps because they just want you to ignore the straps. You're not worrying about any force that they exert. Now here we have a different situation because here we're talking about the top of a loop, not the bottom of a loop. Fw equals mg. And now look at centripetal force. Centripetal force is always directed towards the center of the circle. But in this case, Fw is helping. FW is helping because down happens to be directed towards the center of the circle. FN is also helping because FN is always acting upward on the person who's sitting down, right? And upward, in this case, coincides with towards the center of the circle. That's why we have FC equals FW plus FN here. The setup then is MVT squared over R equals mg plus 1/2 mg. How do we know the 1/2 mg? Well, we get that from the givens. It says that it's going to be half his actual weight. Now, keep in mind that the force exerted by his body on the seat is equal and opposite to the force exerted by the seat on his body. I'll say that one more time. The force exerted by his body on the seat is the same magnitude, yet in the opposite direction, as the force exerted by the seat on his body. Okay, and that's why we're using Fn here and giving it a magnitude of 1/2 mg. Now we can keep it in symbols for the next few steps. That's convenient. And then we can just plug in the numbers at the very end. And so we do that here, and we get a tangential velocity of 19.2 meters per second. Number 26. A stunt pilot flying an old biplane climbs in a vertical circular loop. While upside down, the force acting upward normally on the seat is 1/3 of her usual weight. If the plane is traveling at that moment at 300 kilometers per hour, what is the radius of the loop? A World War I pilot did this little trick without fastening his seatbelt and, you guessed it, fell out. What can you say about his speed at the top of the loop? Okay, so let's answer the first question. We want to find out the radius of the loop. So look at how the setup is similar to the last problem. Since we're dealing with the top of the loop, we have FC equals FW plus Fn. The normal force is in the same direction as the weight. Both of them happen to be going down. And so down, when we're talking about the top of a loop, coincides with towards the center of the circle. MVT squared over R equals mg plus 1/3 mg. Where do we get the 1/3? Again, we get that from the givens in the problem because it tells us that. So VT squared over R equals 4/3 g. And then we can continue by doing a unit conversion. 300 kilometers per hour is 83.3333 meters per second. Plug and chug, and the radius is 531 meters. Number 31, moving on to some gravity problems now. Suppose that two identical spheres separated center to center by 1.00 meters experience a mutual gravitational force of 1.00 newtons. Compute the mass of each sphere. So gravitational force equals G m1 m2 over r squared. 1.00 equals 6.67 times 10 to the negative 11th times m1 squared. We know this because m1 equals m2, so we could have done m2 squared. It'd be the same. Over 1.00 squared, and we get a mass of 1.22 times 10 to the 5th kilograms. Number 37. If you can jump 1.00 meters high on Earth, how high can you jump on Venus, where g equals 0.88 g? Better read, g of Venus equals 0.88 g of Earth. Assume the same takeoff speed. Okay, so we do vf squared equals vi squared plus 2as. 0, which is the final velocity, final vertical velocity at the top of the jump, equals vi squared plus 2 negative 9.81 times 1.00, and we get a vi of 4.42945 meters per second. Now we just do the same thing, same equation, but instead of Earth's g, we're going to use the g of Venus. Okay, and so the A is 0.88 of negative 9.81. They gave us the fraction, or the percentage. We know that Venus's G is 88% of Earth's G, so we can just do 0.88 times negative 9.81. And that would get us at 1.1 meters, so we can jump a little bit higher on Venus. All right, let's go on to number 41. Another gravity problem. The acceleration due to gravity on the surface of Mars is 3.7 meters per second squared. If the planet's diameter is 6.8 times 10 to the 6 meters, determine the mass of the planet and compare it to Earth. Okay, so we have our setup, which is an important thing, and got a little sketch here. The mass of Mars, and we have the radius of Mars, and then we talk about something on the surface, and that's why I drew a little M right on the surface of the planet. And we know that mass is going to have a weight of mg right on the surface. And so the setup then is gm mass of Mars over r of Mars squared. The little m is just that mass that's on the surface, whereas a big M with the subscript m is mass of Mars. And that equals mgm. Why? Because when something is close to the surface, even if something is like, a mile from the surface, when you compare that 1 mile to the very, very large diameter of a planet, the 1 mile is insignificant. Okay, so obviously, if you get farther, if you get out to like maybe 600 miles from the surface, then there could be a difference made. But we consider that surface when it's a negligible distance. So that means that the weight of an object on the surface of Mars is due to gravity, for which we know the equation of gravitational force. Now we do some canceling, so the m's cancel. This, by the way, is why things fall at the same rate, no matter how heavy or light they are, because that m, the little m, that is the mass of the falling thing, cancels out. All right, so now we do a little rearrangement. We do some plugging and chugging, and we get 3.7 meters per second squared. This means that, 3.7 meters per second squared was a given, and we're using that to find the mass of Mars, which is 6.4 times 10 to the 23rd kilograms, which is about 11% of Earth's mass. This means that you can jump quite a bit higher on Mars than you can on Earth. In fact, there was a kind of goofy Disney movie that was made years ago about some guy on Mars who travels between the two planets, and he's able to jump super high on Mars, and he can even win battles because of his high jumping on Mars. But I digress. All right, so let's go on to number 45. Venus has a diameter of 12.1 times 10 to the third kilometers and a mean density of 5.2 times 10 to the third kilograms per cubic meter. How far would an apple fall in 1 second at its surface? Okay, so what we have to do here is we have to look at the radius of Venus. And so the radius of Venus then is going to be 1/2 times that diameter, right? And then we do the times 1,000 because we want to get the meters. Now the volume of Venus would be the volume of a sphere, 4/3 pi RV cubed, equals 9.275817 times 10 to the 20th cubic meters. Now the density of Venus equals the mass over volume. And so we are solving for the mass. We know the volume. And they do also give us the density. So now we can just solve for the mass of Venus. And solving for the mass of Venus, we have 4.82345 times 10 to the 24th kilograms. Now, the g of e, the little g of e, is going to equal g mv over rv squared. So little g always equals big G times the mass of a planet times the square of the radius of the planet. This is true of Venus, true of Earth, is true of every planet. Then we have 6.67 times 10 to the negative 11th. We're doing just a whole bunch of plugging and chugging now. We find out that the G of Venus is 8.79 meters per second squared. And now the original question is, how far would an apple fall in 1 second at its surface? Now, obviously, common sense would tell us that if something's on the surface of a planet, it doesn't fall, right? But they don't mean actually sitting on the surface. They mean that anywhere, within a few miles of the surface. So then we use our equation, Sy equals VIYT plus 1/2 AYT squared. We plug in the 8.79 that we found. Of course, we're going to use it as an A, right? That's why we make it negative. And we know it's exactly 1 second. So that's not going to affect our significant figures. And our final answer is negative 4.4 meters. Number 51. Mars has a mass of m equals 0.108 m. Better read. Mass of Mars equals 0.108 times the mass of Earth. And a mean radius r of Mars equals 0.534 times the r of Earth. Find the acceleration of gravity at its surface in terms of GO. And they're just saying GO because that's like the reference G, 9.8 meters per second squared. Notice that they're not even doing 9.81 here, because it doesn't matter for this problem. Okay, so the G of a planet equals the big G times the mass of the planet divided by the radius of the planet squared. So then we have things that we can plug in. Notice what we plug in for right, mass of Mars. They told us that mass of Mars is 0.108 ME, so we just leave that in. They also told us that radius of Mars is 0.534 radius of Earth, so we put that in too. And then things simplify so that we're left with 0.108 over 0.534 squared times GME over RE squared. Notice that GME over RE squared is big G times mass of Earth divided by radius of Earth squared, which is the same as little g. Little g for Earth, that is. Little g, which we're calling GO or G naught in this problem. And so the final answer is 0.379 GO. Number 62. Using the data for the Earth's orbit, compute the mass of the Sun. Now, I did give you the data that's required for this problem, and that is that Earth's distance from the Sun is 149,600,000 kilometers. So that's enough information for us to figure things out. And here's how. We have mvt squared over r, mass of Earth times its tangential velocity squared over r. Now, this r, of course, would refer to Earth's distance from the Sun. And that's going to equal the gravitational force that supplies it. Remember, mvt squared over r represents the magnitude of the centripetal force. But we also have to talk about what supplies the centripetal force. Could be friction, could be tension, could be normal force, could be a lot of different sources. In this case, it's gravity. Now we cancel some things out. We end up with Vt squared equals G mass of the Sun over R. And we can figure out Vt because we know how long a year takes. If we wanted to be real precise, we could do the 365.24 days, but we're just doing the regular 365 days. So 2 pi r, we're basically considering this orbit a circle, even though it's actually an ellipse. But 2 pi r is a good approximation for the distance that it travels. So it does the total orbit around the sun, approximating that as a circle. It does that huge big circle in 365 days. So then we just plug things in that we know. We plug in the 149,600,000 kilometers. Notice that I'm putting it as meters, so I've already multiplied by 10 to the third. And then I divide by the days, but those days have to be converted to seconds. That gives me 29,806 meters per second. That's how fast the Earth is traveling right now. That's very fast. Now, we have to square that. So what we have here is VT squared equals G m sun over R. Basically, what I did here is I went right back to this spot, and that was based on the original setup. So VT squared equals G mass of sun over R, R being the distance between the sun and the Earth. And now we put these things in again, and we can solve for the mass of the sun. 1.99 times 10 to the 30 kilograms. Number 63, determine the approximate speed of a lunar orbiter revolving in a circular orbit at a height of 62 kilometers. Take the moon's radius as 1738 kilometers. Notice that I also told you as part of the information for this problem, I gave it to you in the list of problems. I told you that the moon's mass is 7.35 times 10 to the 22nd kilograms. All right, now look at what we do for R. Let me explain this. So this M right here would be the center of mass of Earth, or sorry, of the moon. So this is the center of mass of the moon, okay? And then of course, there is a radius of the moon, but there's also an altitude of the satellite. And that altitude is a significant portion of the moon's radius, and therefore we can't neglect it. It's not negligible. So that has to be figured into our total R for this orbit. R equals 1738 kilometers plus 62 kilometers, which equals 1,800 kilometers, which equals 1,800,000 meters. Now, this next part basically says that gravity supplies centripetal force. We've got on this side here, we've got the expression for gravity, G m1 m2 over r squared equals m2 vt squared over r. So left side, we're talking about what supplies the centripetal force. Right side, we're talking about magnitude of centripetal force. And we can set them equal to each other. Now, canceling out, we get gm1 over r equals vt squared. Plugging and chugging, we get vt squared, and we find vt to be 1.65 kilometers per second. 1.65 kilometers per second. All right, hopefully that helped. As always, as I said before, you should really just be using the videos as a help when you get stuck or when you want to check your answers. Never use them as a crutch because that's counterproductive. All right, see you in class.